All right, good morning, everybody. I am here to finish up the urinary system today. Primarily, what I'm going to talk about is something called the countercurrent multiplier, which happens with the nephron, specifically the nephron loop in the nephron. It's a really complicated thing to discuss. It's a complicated thing to comprehend, and I am planning to post, not planning to post, I am going to post some videos from YouTube that I think are helpful. I apologize. I thought I posted them last week, but I didn't. So as soon as I'm done today, I'm going to post some videos, some YouTube videos to Moodle that will hopefully help to explain some of this to you guys. So let me go ahead and share my screen, and we can start talking about countercurrent multiplication. Countercurrent multiplier, a lot of times it's called. So within the nephrons, right? We said there's millions of nephrons in each kidney, and that's where the actual filtration takes place. There is this thing called countercurrent multiplication. Countercurrent means there's exchange between fluids moving in opposite directions. So there's an exchange between the fluid in the nephron and what is around the nephron, which is called the peritubular fluid. And that exchange causes an effect within the peritubular capillaries, or within the peritubular fluid, which is in the adrenal medulla, or the renal medulla, to cause this difference in salt concentration. So this occurs between the two parallel limbs of the nephron loop, the descending limb and the thick ascending limb. And what you may have noticed when you're looking at some of these diagrams, the descending limb is always drawn very thin, the ascending limb is thicker. Okay, and that's purposeful. There's a reason for that. These segments are really close together. The only thing separating them is peritubular fluid. So there's the descending limb, the thin descending limb, peritubular fluid, the thick ascending limb. And the permeability is very different. That means that what gets in and out of the descending limb is very different than what can get in and out of the ascending limb. Right? The descending limb is very permeable to water, but not very permeable to solutes. So what that means is that water can get across that descending limb, but salts can't. Then you have a thick ascending limb. The thick ascending limb is relatively impermeable to water and solutes. So neither water nor solutes can actually get in or out of there very easily. However, it does contain active transport mechanisms, like the sodium pumps and the chlorine pumps. So the overview of this, the overall big picture, is that sodium and chlorine, actually sodium and chloride, are pumped out of the thick ascending limb. This elevates the osmotic concentration around that thin limb. Water flows out of the descending thin limb and into the peritubular fluid, and that increases the solute concentration of the tubular fluid in the descending thin limb. So then what arrives in the thick ascending limb is a concentrated solution with a lot of sodium and chloride, and the solute pumps out of the thick ascending limb. So let's see if I can get to a picture. This is better. This is easier to see. So what we have here is the descending limb and the ascending limb. So let's say the concentration inside your nephron in the descending limb up here is about 300 milliosmolars per liter. As fluid travels down this descending limb, water is diffusing out, right? Water is permeable. So this goes from being 300 to 600 to 900 to 1200, right? The osmolarity, this gets more and more concentrated. As water's flowing out, what you're left with in here is more and more salt, right? So there's a certain amount of salt and water in here. If you keep taking away water, the salt becomes more concentrated. By the time you get down to here, it's highly concentrated. Now, as this fluid moves back up the ascending limb, what's happening is the sodium and the chlorine are being pumped out, right? And so the salt, there's a lot of salt in here, the salt's being pumped out. So by the time this fluid gets back up to here, it's back to kind of a low osmotic pressure again, or a low osmotic gradient. The result of that is that all of this pink space around this tubule, this is called the renal medulla, right? This is the inner part of the pyramids, has a concentration, an osmotic concentration of about 300 at the top. Down at the bottom, it's about 1200. What that's saying is that as you descend through the renal medulla, we're not talking about in the nephrons at all. We're talking about outside the nephrons, in the medulla. As things descend through that medulla, there is an increasing salt concentration. Okay, it's called a countercurrent multiplier because you have fluid moving one way and then fluid moving the other way, and it just multiplies this effect. What it's doing is it's multiplying the effect of making the fluid at the top here, near the top of this medulla, less concentrated with salt, less full of salt, and the fluid at the bottom is more full of salt. So what happens then is this is your nephron, right? And it's attached to a collecting duct. The collecting duct is moving through that same renal medulla. The collecting duct is moving through a renal medulla that goes from being less concentrated with salt to being more concentrated with salt. And the collecting duct is impermeable to urea, but it has variable permeability to water. So what this is going to affect is it's going to concentrate the urea in the tubular fluid and in the medulla. And so what happens is the collecting ducts are impermeable to urea. So urea can't get out of there, right? So urea ends up going to your urine. It travels through the collecting duct to get through your bladder. This affects also how much water is reabsorbed and how much ADH is what the effect of ADH has. Okay, so ADH is the hormone that causes insertion of aquaporins into apical cell membranes. What ADH does is it increases the osmotic water movement. So without ADH, you're losing water, right? It's going into the urine. But with ADH, water can get out of the collecting duct and you end up retaining that water. So in the presence of ADH, water is moving out of the distal collecting duct. The tubular fluid reaches about 300 milliosmolars per liter. And then in the minor calyx, it approaches 1200, depending on how much ADH is present. So you end up with this big difference between the osmolarity here and the osmolarity down here. So here you can see, right, in this picture here, you can see the permeabilities without ADH and then with ADH. So what ADH does is it allows a lot more water to come out of this collecting duct, and that will allow you to retain water, right? And that means that what's left in this collecting duct is mostly salt. It's mostly concentrated. So your urine would be mostly concentrated with solutes or salts, and there would be a lot less water in them. So how is this regulated? Well, your hypothalamus is what secretes low levels of ADH. We know that, which makes the DCT and collecting system always permeable to water. So you always want to hold on to a certain amount of water. You don't want to keep passing that through your urinary system. The vasa recta are just the capillaries that surround the nephron loop. right? So they're called peritubular capillaries because they're surrounding the tubule. In particular, the vasorecta are the peritubular capillaries surrounding the nephron loop. What they do is they take that reabsorbed solutes and they put it back into your general circulation. So they are surrounding the loop, the nephron loop, and they are reabsorbing nutrients from the nephron, and they're putting that back into your blood. So again, we talked about this when I drew this last week, or in our last lecture rather. But step one is in the glomerulus. That's glomerular filtration, right? Too much stuff is squeezed out in the glomerulus. Step two, the proximal convoluted tubule, is where you start to reabsorb a lot of those nutrients back into your bloodstream. Step three, in the proximal convoluted tubule, you actually go the other way, right? Water moves into the peritubular capillary, into the peritubular fluid, rather. It's moving out of the bloodstream. And then step four is that you have a thick ascending limb. Tubular cells are actively transporting sodium and chlorine out, sodium and chloride out. Step five, distal convoluted tubule makes further adjustments in composition of tubular fluid. Step six is the distal convoluted tubule and collecting system. Step seven, the vasorecta absorbs solutes. Step eight, the papillary duct is permeable to urea. Right, and here is all of it. So, I went fast through that, so I want to go slower through this picture. Right, here is the blood vessel going into Bowman's capsule. Right, this is your nephron in white. This is the renal corpuscle, which includes Bowman's capsule and the glomerulus. So step one, the filtrate produced by the renal corpuscle has the same osmotic concentration as plasma. So that 300, that number, is about the same osmotic concentration as what's in your blood. But what's going to happen is now, as that fluid travels through the proximal convoluted tubule and down the loop of Henle, or down the nephron loop, I should say. As it travels down the nephron loop, what's going to happen is water is moving out of it, right? And so you can see that the tissue surrounding the descending limb of the nephron loop gets more and more concentrated. Right? Then as it moves its way back up the ascending limb of the nephron loop, water is no longer permeable, but sodium and chlorine get pumped out. So salts get pumped out. So as you go from being highly concentrated with salt, as you move up this ascending limb, the salt is being pumped out and the osmotic concentration becomes lower. It comes back to about what you started with, right? So this 300 is what you started with over here. So nothing is happening to the osmotic concentration, essentially. As it's going through the nephron, the osmotic concentration is going way up and then way back down. But it started at 300, it's ending around 300 when it gets to here. But the difference is when it goes down this descending limb and back up the ascending limb, you are creating this osmotic concentration in the tissue around the nephron. Then that fluid is going to travel through the collecting duct, right? That's to travel back to or down to the bladder. And as it's traveling through there, water is being taken out, right? Your body's making ADH, which is allowing water to get out of this collecting duct. And again, by the time the water reaches, or by the time the fluid reaches the bladder, it's going to, or not even the bladder, by the time it gets to the end of the renal pyramid, right, and the minor calyx would be right here at the end, it's back to about a 1200 in terms of osmotic concentration, because you've lost a bunch of water again. So what's really in this urine is mostly salt. Okay, so the The composition of urine reflects the filtration, the reabsorption, and the secretion activities of the nephrons. Some substances like urea is neither excreted nor reabsorbed. Urea can't get across that. But there are other organic nutrients that are completely reabsorbed. Okay, and so one of the first things the doctor will ask you to do when you go for a doctor's visit is to pee in a cup. And it's because that can tell the doctor a lot about what's going on with your body. So normal urine should be clear and sterile. There should be some concentration of substances in there due to the osmotic movement of water across the walls, but you shouldn't have a high concentration of a lot of things. The yellow color is due to a pigment called urobilin, which is generated from your kidneys. It has to do with getting rid of bile. Urinalysis is the analysis of a urine sample, which is an important diagnostic tool. And here are all the things that they analyze, right? So when you pee in a cup, not only do they look at the color of it, but they check the pH of it. It's pretty easy to do. They check, what percentage of it is water. Is there a lot, is there a lot of salts in there? Is it, does it have an odor to it? Is there a bacterial content in it? Is it cloudy? Right? So all of these different things can indicate different problems. For instance, creatinine clearance compares the creatine level in your urine with that in your blood. It's used to estimate what the filtration rate of your glomerulus is. A more accurate glomerular filtration rate can be obtained using insulin, and insulin is a carbohydrate that is not metabolized, so you can see how fast that filtration rate happens. Right? They can also do a blood urea nitrogen test, which measures the amount of urea in the blood, which should be low because urea should get filtered to your bladder, so there shouldn't be much of it in your blood at all. So then we get to kind of the transport, storage, and elimination of urine, right? Again, you want the urine to be transported and stored in your bladder, be eliminated by your bladder, right? This is a picture just showing, this is the urine leaving the kidneys. So these are the minor calyces and major calyces, renal pelvis, ureter, down to the bladder. And the ureter are muscular tubes that extend from the kidneys to the bladder, and they enter the bladder through uretic orifices. Each ureter, has 3 layers: an inner mucosa, the middle, which is the muscle layer, which pushes urine through there, kind of like peristalsis in your digestive system. And the outer layer is a connective tissue layer. So there you can see it. It's cross section through a ureter. And like I said, you get those peristaltic contractions. So the muscle contracts, pushes urine from your kidneys to your bladder. Your bladder is just a hollow muscular organ where the urine is temporarily stored, right? And the bladder position is posterior in your lower abdominal cavity, or your abdominal pelvic cavity, right? It is anchored by ligaments, right? So it's anchored to the bones around it by these ligaments, and you can see the difference between the male urethra, the male bladder, right? The bladder's here. The urethra has to travel through the penis and out through the body that way, whereas from the female bladder to the exterior of her body, the urethra is only maybe ½ an inch long. The bladder does also have umbilical ligaments, which extend towards your navel, right? And here is a cross section through the bladder, right? These 2 uretic orifices, those are where the ureters come in. So here's a ureter, comes behind the bladder, and this one comes behind the bladder. That's where they're sending urine into the bladder, right? The bladder can actually expand to accommodate more and more urine. Then the area where fluid leaves is called the neck. It is on both sides flanked by a sphincter, or it's a round muscle basically. It's called the internal urethral sphincter. The internal one is smooth muscle. You can't control that. It's not voluntary. This is a male bladder, obviously, because the prostate is right there. And in the male, the urethra goes through the prostate, right? And on the other side of the prostate is where the external urethral sphincter is. That's the one that you can voluntarily control. So that's the one that you learn to control as a baby. All right. So I think, I mean, then we can talk about there's the female, right? The urethra transports the urine from the neck of the urinary bladder to the exterior of the body. As I talked about, the male urethra is longer because it has to go through more structures. And the male urethra is divided into three parts: the prostatic urethra, which passes through the prostate; the membranous urethra, which is a really short segment that just goes through the muscle of your pelvic cavity, basically. And then the rest of the urethra is the spongy urethra that goes all the way through the penis, right? So the prostatic urethra is just this little part in the prostate. The membranous urethra is the tiny little part right here through this muscle. And then the majority of the urethra is the spongy urethra, which travels through the penis. The female urethra is very short, right? It just extends. There's not three segments to it. It just extends from the bladder to the outside. But in both sexes, there's an external urethral sphincter that's under voluntary control. This is the one that we learn to control as a baby. So I think you guys will be good on all of that stuff. Now, what I do know is that the countercurrent multiplier system is something that is more involved and more in depth and a little bit more of a complicated thing to get through. So I'm going to go ahead and post this, but I'll also post a few YouTube videos that I think explain this countercurrent mechanism really well, so that you can watch those as well. And I would ask that any of you guys that have questions, just please send me an email with those questions. And what we'll do on Monday is we'll go through the next chapter, which is about like acid-base balance. So it's just a continuation of this chapter of how you are balancing a lot of these nutrients and these solutes in the urinary system, because what you're doing is you're balancing how much of them get passed to your urine and leave the body. So that regulates a lot of the homeostasis in your body. All right. So everybody have a great weekend, and I will talk to you soon.